Hello students, welcome to today's session of chemistry. As you all know, we have started with 8th lesson of your syllabus, that is transition and inner transition elements. We call them D block elements and F block elements. In the previous session, we have started with transition elements, that is D block elements, and we learned about position of these elements, their electronic configuration. In short, we have been introduced with transition elements in previous session. We will just revise some points. Now, as you know, D block is placed at the center of the periodic table with electropositive strong metals on the left side and electronegative non-metals on the right side. That means in left side S block is there and to the right side P block is there and F block is at the bottom of the periodic table. That means D block is at the center of the periodic table and all the properties are transmitted from S block to P block through D block, and hence they are called as transition. The properties are transited, hence these are called transition elements. What kind of elements are there in the D block? Do you remember? All are metals because metal property goes on decreasing from left to right, but all the elements those are in D block are metals. Again, we learn about there are 10 different groups because D has the capacity to accommodate 10 electrons. Every time as we move from left to right, nuclear charge increases by 1 unit. And these elements are located in 4 different series depending upon in which D subshell the electrons are accommodated. That means 3D series, 4D series, 5D series and 6D series. Now, in today's session, we are going to learn about the oxidation states shown by these elements and the periodic trains of these elements. Now, oxidation states we are going to start with. So, oxidation states of first transition series we are going to see in detail because I have told you earlier that 3D series in elements, our first transition series elements are there for study representing transition elements. So, detailed study of 3D elements is there included in your syllabus. So, first transition series and its periodic trains and detailed study we are going to see in this lesson. Now, for oxidation state, we require its electronic configuration. And do you remember general electronic configuration of 3D series? It is this. What is oxidation state? We know it very well. Oxidation state is the number of electrons lost or gained while forming a compound by that element. As D has a capacity to accommodate 10 electrons. Hence, these elements show variety of oxidation states. So variety, that means number of oxidation states or number of compounds formed by these elements are many. So they display a variety of oxidation states in their compounds. If one of the 4s electron is lost, as the electrons is lost, that means donated, so it will form M plus ion. If one of the electron is lost, if 2 electrons are lost, then what will happen? It will form M plus 2 ion. Now D sublevel will start and this D subshell has 10 electrons and which can be donated because as we know, first the D orbitals or any orbital is singly occupied and then the pairing starts. Hence, it can donate 3 electrons, 4 electrons, so loss of 3 electrons and 4 3D. If one of the 3D electron and 2 4s electrons are lost, it will form F plus 3F. If along with 2 electrons of 4s, if it loses 2 D electrons, then it will form M plus 4 ion. Like that, M plus 5 ion, M plus 6 is also possible by donating 3d electrons which are unpaired and which are there in the last shell. So, because of variety of oxidation states, it forms number of compounds. So, as the number of unpaired electrons in the 3d orbital increases, the number of oxidation states shown by the element also increases, because 3d, as we move from left to right, from scandium to zinc, one proton and one electron is added. Scandium 21. Then second element, titanium, it has two electrons in the d cell. Thus it will show again number of oxidation states shown by this element will increase. Let us see at a glance all the variety of oxidation states shown by these elements in a tabular form. So this is the table showing oxidation states of first transition series elements. These are the elements from scandium up to zinc, and from 21 we can say 21 to 30, and 4s is already completed, and the electron when it starts filling d subshell, then d block starts. Hence scandium has only one electron in d sublevel and 4s has two electrons. So if the two electrons from 4s sublevel subshell are donated, then it will show plus 2 oxidation state. And while forming compound, if all the 3 electrons are donated, then it will show plus 3 oxidation state. So it can show plus 2 as well as plus 3 oxidation state. Understood? Okay, let us consider second example. Titanium, atomic number 22, last shell, 4s, has 2 electrons, subshell 3d, penultimate shell with 2 electrons. Now, if 2 electrons of 4s are donated only, then it will show plus 2. If one of the electron from D, because D has 5 orbitals with 2 unpaired electrons in case of titanium. So those 2 electrons can be donated one by one. If one of the electron is donated, it will form plus 3, and if both the electrons are donated from D, then it will form plus 4. That means plus 2, plus 3, plus 4 are the possibilities, are the variety of oxidation states shown by titanium. Like that, vanadium, it can show one more electron is added in the 3d subshell. That means it shows along with plus 2, plus 3, plus 4, it can show plus 5 also if all the electrons are donated. Chromium likewise can show plus 2, plus 3, plus 4, plus 5, plus 6, these number of oxidation states, because all the 3d levels now are singly occupied, and 4s can also be donated, and then only 3d electrons can be removed. That means all the variety of oxidation states shown will be more in case of chromium. Manganese in this series shows highest number of oxidation states. That means it can donate 2 electrons from 4s, 1 from 3d, 2 from 3d, 3 from like that, 3d 5, 4s 2. So all the singly occupied 3d sublevels are there and 2 electrons in the 4s sublevel. So it can show maximum number of oxidation from plus 2 to plus 7. Now, one more extra electron in case of iron. Iron, that extra electron will go to first 3d sublayer. Well, that means pairing will start now. Now only 4 unpaired electrons are there in the last shell. Those 4 electrons and 2 from 4s. So maximum oxidation state shown by iron will be plus 6 and not plus 7. Because manganese has all the d electrons or d orbitals are singly occupied, but iron has only 4 singly occupied sublevels and one is paired. That means total plus 2 to plus 6. Now cobalt, one more electron is added and it will occupy second sub shell or second orbital of subshell 3d, and hence it has 3 unpaired electrons in d and 2 in 4. So that means maximum plus 5. Like that, when we come to zinc, it shows only one because 3d is fulfilled. All the suborbitals are paired. They have paired electrons, and in electron cannot be removed from stable, fulfilled, completely filled sublet. S can easily donate the electron. It is fulfilled. Still, it can donate because it has lesser energy. It requires less energy to remove electron from the last shell. So, for S, only 2 electrons can be donated by zinc, and hence zinc shows only one oxidation state plus 2. Now, from this table, few points can be we can collect. As we move to the center of the series, the number of oxidation states goes on increasing. The highest number of oxidation states showed by manganese. So let us study, or we can collect these points. From that table, we can conclude that scandium has only one unpaired electron. D has only one unpaired electron. Hence, it shows only two oxidation states. That is plus 2 and plus 3. 2 from 4s and 1 from D. So, plus 2 and plus 3, only two oxidation states are possible for scandium. While manganese with 5 unpaired D electrons shows 6 different oxidation states from plus 2 to plus 7. The elements which give the greatest number of oxidation states occur are in or near the middle of the series. And then again, declining star, that means number of oxidation states. From middle to last, they are decreasing. So, at the center or in the middle of the series, the number of oxidation states shown by those elements are highest, with manganese showing highest number of oxidation states from plus 2 to plus 7. Now, we will see the physical properties of transition series. We learned in detail about oxidation states now. Now, physical properties of first transition series. Physical properties, those include melting point, boiling point, their state, their hardness, their density, their melting. So, we will study in detail about physical properties. Now, we have seen that D block elements are all metals. So, these elements show typical metallic properties. Which are those? You know them very well. First is they are hard, metallic properties. They are lustrous. Their outer surface glitter, that has luster. So they are malleable, they are ductile. So we can prepare thin sheets. We can draw wires from that. So they also form alloys with other metals. What is alloy? That is, when two solids combine, the mixture of these two metals is called alloy. So, these are typical metallic properties. They are hard, lustrous, malleable, ductile, and they can form alloys with other metals. Another property, you know it very well, that is, they are good conductors of heat and electricity. So, there are four exceptions, which are zinc, cadmium, mercury, and manganese. They don't show typical metallic properties, or they are exceptions to metallic properties. Okay. So, next. These transition metals are very hard and have low volatility. Low volatility, we know all these volatile elements. These are, as they are in solid state, no problem of volatility. But with zinc, cadmium, and mercury, they are not as hard as that of other metals. Mercury, we know at room temperature it is in liquid state, but volatility is very less. But these are soft metals, we can say. All these metals, again, because of hardness, they have high melting and boiling points. So these are the physical properties of first transition series elements. They are typical metals, displaying all metallic properties. Now, about periodic trains of these elements. Periodic trains we will see in the next video, because now this is the time for assignment. So, first question will be, write down the oxidation states of first scandium, then manganese, third is iron, and last one is zinc. So write down the oxidation states shown by scandium, manganese, iron, and zinc. Next question will be write down the physical properties of first transition series. Thank you.